Good afternoon. This is Schweitzer. We're going to look at a pretty common scenario here where we of what's called a river bolt problem. I'm going to cover two problems here and kind of take a look at how they might operate. Obviously, at this point, you should be, if you can, trying your own first, but as always, follow along. So we have a boat here crossing a river 50 meters, as seen below. The boat can only travel 1.5 meters per second. Okay, so this river is flowing faster than this river. Okay, so the question is, a couple of questions really that could possibly come out of this is one, how which boat gets across the river first? Okay, um, how far down the river does each boater travel? What is boater's a vector notation velocity? Okay, and key idea here, okay, that we're looking at here and trying to reiterate is that we have an x component and we have a y component, two different velocity vectors, and they work separately. Okay, so when you're traveling in the x direction, you're only taking advantage of the x component. When you're in the y direction, you take advantage of that direction, just like throwing a rock off a cliff. You have this x velocity going this way, and you have a y direction going that. They're going to work completely separate. Okay, so either way, let's take a look at what we got here, and let's try it out. Okay, so who gets across the river first? As I mentioned, they're running individually. So main formulas we're looking at here would be xt equals xi plus vit plus 1/2 at squared. My distance here is 0 to 50. So this is going to be 50. This is 0. My velocity, I'm going to put just, well, it's 1.5. And then there's t, it's the time it takes to get across, and there's no acceleration. So at this point, we have t, time it takes to get across, is going to be, now you notice here, both boulders have the same distance traveling, and they have the same velocity across that distance. Now this guy is going to take a little more steeper route, and this one's a more shallower route, but the same distance traveled, same time. Therefore, the time's the same. So who gets across the river first? It is the same. It is the same. Now, this guy's actual inline path is longer, but he's also traveling, that inline velocity is faster because the river's going faster. So either way, the time in this case is 33.3 seconds. All right, how far down the river do we go? So again, like we're trying to really reiterate here, these two components are completely separate. So once again, I'm going to go yt equals y initial, or y0, plus vit plus 1/2 at squared. Okay, so what do we got here? The distance down, this is really what I'm looking at. I want to find yt equals 0. That's going to be my reference point. Initial velocity, it's asking for how far down the river. So let's just put in this guy first. 0.75 is my velocity of the river, and the time is 33.3. And the acceleration is 0. So the other guy, for A versus B, it's going to be 0. All right, so that's out, plus 2.5, and then times 33.3. So then they're water the same amount of time, but the B is traveling faster, several times faster. So let's just punch this out here quickly, calculator-wise. So we got our answers. 0.75 times 33 equals 24.75. So this guy's in 24.75 meters down the road, and this one is 33.3 times 2.5 is going to be 83.25. 83.25. Okay, this is just in meters, so pretty standard question. Last thing we got here on this guy here is, what is the boulder's A's vector notation velocity? This is sort of a term, I sometimes call it inline. Like, what's the actual inline velocity? right? Vector notation velocity, okay, now we have a velocity going this way that is 1.5, and I have a vector going this way, which is smaller, so because it's 0.75. So, and this is the actual inline speed or velocity. So I have a adjacent and I have an opposite for this angle right here. So let's use Pythagorean theorem to get this inline velocity. 1.5 squared plus 0.75 squared square root this guy, and the velocity in line is equal to, all right, 1.67 meters per second and 1.67 meters per second. Okay. Now we need an angle too. A vector has a magnitude and an direction. So let's get that angle here, right there. So I'm going to use the tangent function because I have everything I need for tangent. I could use any, at this point I have all three sides. I could use whatever, sine function, cosine function, but I'm going to use this guy. And its opposite, which is 0.75, over the adjacent, which is 1.5. And we're going to solve it out, divide out, inverse tangent both sides. This division is 1.5, or sorry, 0.5. So it's going to be the inverse tangent of 0.5 is just 26.5 degrees, which seems like that's about right. 26.5 degrees, and you could put, down from the horizon, or however you want to, list that out. All right, so here's a second little problem here. Okay, so now we're adding a little bit different scenario here. We got a river, same river. Okay, and let's make the river traveling at, let's use river B this time, 2.5. All right, meters per second rolling that way, and the river's still 50 meters across. Okay, so it's 50 meters across, and but this time boulder B cranks it up and has an angle up of 20 degrees. Okay, and it's traveling 3 meters per second. 3 meters per second. So this is a pretty common scenario here where now, again, I need to know what are all my x components, because they're going to work differently than are my y components that are traveling this way. All right, so my y component is just the river, but I'm going up and down here. So this 3 meter per second has two components. Has an x component and it has a y component. Now, and the angle is 20 degrees. So this is a unique situation. Okay. First of all, let's figure out how much time does it take for me to actually get across this river. I need to know my x component. So what is my x component? Well, breaking apart this thing into two different components is a pretty valuable skill and something that we're going to use a lot. Let's break it apart into its x and y quickly here. So this guy here, x component, as we've mentioned kind of hopefully in the past, and I'm trying to say this is shortcut would be the magnitude of, so this is the cosine function, the magnitude of the vector times the cosine of the angle equals my x component. How did I get that? Okay, well the cosine, I'll repeat it again, cosine of the angle is the adjacent over the hypotenuse. Hypotenuse is the magnitude of that vector. So multiply across, and I got that. Okay, so it's going to be 3 times the cosine of 20 equals my x component. Now I only need my x component in order to find the time it takes to get across the river. All right, so 3 times the cosine of 20, and I got 2.81 meters per second. All right, so x equals 2.81 meters per second. Okay, so now time it takes to get across the river, we'll just do this. Xt equals xi plus vit plus 1/2 at squared. There's no velocity and xi is 0. So distance is 50 meters, is traveling in x, equals vi, which is now 2.81 meters per second. And then there's the time. We can solve for that. Okay, 50 divided by 2.81. 50 divided by 2.81 equals 17 point almost 8. So t equals 17.8 seconds. All right, so now our last question I'm just going to throw up here would be, how far downriver, or are we even going to be downriver? Maybe we'll be upriver. Maybe we'll be exactly horizontal. Where are we on this thing? Okay, great question. But now we need this component, this y velocity. This is going to be the magnitude of the vector times the sine of the angle. Okay, will give me my y component. I did the same thing with the sine. All right, the sine of the angle is equal to the opposite divided by the magnitude of the vector, which is the hypotenuse. All right, so let's solve it out. It's 3 times the sine of 20 equals. Okay, so we have, in this situation, 3 times the sine of 20 degrees. And this is giving us 1.02. So will we end up upriver or will we end up downriver? We're going to end up downriver because we have two vectors. Now this is great vector stuff here. We have a vector that's going up at 1.02, basically 1, and a vector going down at 2.5. Let's add those two vectors together because they're in line. We can just add them up, head to tail. Put head to tail. Now my head is by my tail, and they just cut each other off, subtract. And my new vector is down at, I'm just going to go 1 at that guy, so it's going to be 1.5 down in that direction. So how far down do I go? Yt equals y initial plus vit plus 1/2 at squared. And of course this is 0, this is 0. Looking for this value, and I'm just going to use the 1.5, and my time is 17.8 seconds. And at that point, our video is basically over. 17.8 times 1.5, and I got 26.7. So I'm down the river 26.7 meters. Okay. It would be possible to solve out for, what at this angle, what velocity would I need so that I can get all the way across the river and end up over here. Okay. So that would be an interesting problem. Sometimes they get a little more complicated, which really doesn't always benefit us from getting from point A to point B. But there's all sorts of different things. Okay. You could also solve for the angle it takes for 3 degrees, solve for the angle that would require to get across the river. All right. Thank you very much.